if they want to see the problems again. So, let's see. Over. So here's the practice set of problems. We've been looking at those. Oh, it's moving again. On Wednesday, same hours of class, 4:20 to 5:35. We'll have exam 2. It's going to cover chapter 6 only. And problems similar to the homework. So if you look through your homework sheet, all the problems, I'll just make like some of those. There is a set of practice problems online, as I announced last time. Most of them will be similar to the practice problems, but not all. Labeled practice, Trig practice 2.6 or something like that, but it's practice example 2, version 6 is the idea. So, you do need a calculator for parts of it. It would be nice to have a graphing calculator so you can check some of your answers, but you're not required to have a graphing calculator. You can do them all without it, but you might need a calculator to just do the numbers. But you will need a calculator to do some of the numbers. And then it's online by email, just like last time. So hopefully we're practiced at it now. It won't be quite so bad. By email, arriving around 4:20. And then return it to the same email address. Open book, open notes, just like last time. But no human can help you. and computer, you can use your computer, but no online people. I think if there's any other comments we should make about the test itself, I think that pretty well covers it. It'll be shorter than the practice test, but the same style.
Is it shorter?
Yeah, shorter than the practice test set, yeah. Okay, any other questions about the test in particular? Don't show up here. It'll be all by email. If you want to sit here with your laptop, you can, but there's no advantage. All right. Well, for today, then, I want to go over some of these problems that we've got on the practice test and any others you have from the homework. Is there anything in particular that's bothering you that you especially like to look at today? I'll take questions online. People on WebEx, if you want, just take the mute off for a second and ask a question, and I'll try and answer it.
Could you do 6A?
Yeah. I'll scroll down on here into the classroom. And here we want to find an exact expression. I don't want a decimal if you're on this in your calculator. By the way, there are some calculators that will do some of these for you. This 6A is exactly the kind of problem I'd like you to do because most calculators won't be able to do this exactly, so we'll force you to do it yourself. So this is an excellent problem in that sense. 6A, evaluate exactly the tangent of the arc cosine, and I'm sorry, that's a little hard to read. I'll try and make it a little clearer on the actual test, but it says x over x plus 1. Right? Now, the trick here is to thought of this a little bit like a cookbook and think if it's this kind of problem, I'll do this. If it's that kind of problem, I'll do that. We have different cases. You take a trig function of its own inverse trig function. It either undoes it, or you can evaluate it in the unit circle to do it exactly. If you have an inverse trig function of a trig function, it either undoes it and gives you the same number back, or it's undefined, those kind of things. In this case, where you have a trig function of an inverse trig function, it turns out these can always be done exactly. So whenever you see trig function of inverse trig, you can do it exactly. By hand, by drawing a right triangle. And here's the steps that we said before. One, you make a right triangle. I say sketch is the best idea. With one angle equal to the inverse trig function that you see. Whatever it is. In this case, it's arc cosine of x over x plus 1. So I'll do that for step 1. It doesn't have to have the right length, just to put the right size on there. So here's a right triangle. I'll put theta in this corner. It doesn't matter which corner. Now I need to make theta to be the arc cosine of x over x plus 1. In a right triangle, the trig function of the inverse trig function always undoes it. So you just take cosine of each side, and you've got cosine theta equals cosine of the arc cosine, undo each other in a triangle. The reason being that the inverse trig functions always undo the trig functions and vice versa in the first quadrant. And right triangles are always first quadrant because right 90 degrees is here, they add up to 180. These are always less than 90. So right triangle angles are always in the first quadrant, and trig functions and their inverses always undo each other in that quadrant. So there it is. I take the cosine of both sides and get cosine theta must be x over x plus 1. So now cosine theta is adjacent over hypotenuse, so I could take this to be the adjacent side, and I could take this one to be the hypotenuse. So I've got adjacent over hypotenuse. This must be x, and this must be x plus 1. Now the second step, I might need to move the camera. Is to do this. Find the last side length by the Pythagorean theorem. So I'll say the last side here, since it's a leg, it's the square root of the hypotenuse squared minus the other leg squared. Right? This is the Pythagorean theorem solved for a leg, if you call it side A or something. A is square root of c squared minus b squared is what that formula is. This is the length of the other side of the other leg. Well, we can simplify this, right? This is foiling. This is not x squared plus 1 squared. What is it? Put it here. When I square x plus 1. I have to FOIL. I have to take x plus 1 times x plus 1 from algebra. And you get x times x is x squared. And then x times 1 is x. And then 1 times x is another x. You got plus 2x. And then plus 1 times 1 is 1 squared. So be careful when you square this. Don't write x squared plus 1 squared. It's x squared plus 2x plus 1. You have to FOIL x plus 1, right? So there's this one. I can erase this now. And then minus x squared. Now x squared and minus x squared cancel. And so this is just the square root of 2x plus 1. Right? 1 squared being 1. That's the last side of the triangle. I can now draw it in. That's not a bad idea. And finally, 3, evaluate the expression using the triangle. All right, so we'll say that the tangent of the arc cosine of x over x plus 1 is the tangent of theta, because we built the triangle that way, right? Theta is the arc cosine. But the tangent is the opposite over the adjacent. So that would be, the opposite here is square root of 2x plus 1. And the adjacent is x. So there it is. And amazingly, whenever you take a trig function of an inverse trig function, that order, you always get an algebraic expression in terms of roots and arithmetic. And so I think that's kind of interesting. You'd think you get something too complicated, but you just get algebra back. There's this one. Well, I might throw something at that like that on the test. That's a really good problem. Yeah.
6E.
Okay. See all the way to the left on the camera. I think I can. That'll be good. Six E asked me to do something different. This is no longer a trig function of an inverse trig function. It's an inverse trig function of a trig function. And so this one works differently when the inverse trig function is on the outside. What happens is you'd like to think these undo each other, and sometimes they do and sometimes they don't. And we recall this maybe, it depends on the range of the inverse trig function. Here's what we said before, is that the arctangent of the tangent of any angle x is equal to x if x is between minus pi over 2 and pi over 2. And it's equal to something else otherwise. So if the angle here is between plus and minus pi over 2, then I just write that angle over here. So first think of that, think, do I need to do anything, or can I just write this number and be done? Because I might give you one like that, right? Just to see if you're paying attention. And unfortunately, it's not, right? This is bigger than pi over 2, so it's too big. I'm going to get something else. So do this immediately. How do we know these are the right angles? A nice way to remember this is if you just remember that when we found the inverse of the tangent function, here's the tangent function. It has asymptotes of plus and minus pi over 2. And when we found the inverse, we took this piece and flipped it. Since we took the piece that goes between angles between minus pi over 2 and pi over 2, that's precisely where the inverse trig function will invert it. So it'll look like this, and you'll always get an angle between plus and minus pi over 2. And so you'll get back what you started with only for those angles from the piece you started with. So this won't help us here. Instead, when you get to something else case, go to the unit circle. If it's a non-special angle, then you'll just have to use a calculator approximation. But in this case, it's a special angle, so we can go to the unit circle. So I'll say, here is the picture. Tangent is actually the hard case. You guys are doing a good job. 3 pi over 4, I sketch it on the unit circle, is pi over 2 plus pi over 4. It's right here. 135 degrees if you prefer degrees. Or you can say it's pi back up pi over 4. There it is. And that leaves pi over 4 here so that these two angles add up to pi, a straight angle. Now I can drop a perpendicular. Get this 45, 45, 90 triangle whose sides we memorize. 1, square root 2 over 2, and square root 2 over 2. So the tangent of 3 pi over 4 is based not on the side lengths but the coordinates. The coordinates are minus square root 2 over 2 since I went left, and plus square root 2 over 2 since I went up. So this is the arctangent then of, for a tangent, it's y over x, square root 2 over 2y over x minus square root 2 over 2, or the arctangent of -1. In other words, the tangent of 3 pi over 4 from this diagram is negative. Now, how do I find the angle between minus pi over 2 and pi over 2 such that the tangent of theta is this number, -1. That's the question when you have to evaluate the inverse tangent. You're right, when you say what's the arctangent of -1, you're saying what angle gives you that tangent, and it has to be between here. There's only one such angle, and you just have to figure out what it is. Well, this means if you want the tangent to be -1, where tangent is y over x, then you need y and x to be minus each other, right? So there's one place here where y is equal to minus x. That's the direction we started with. The other place is way over here in the direct opposite direction. Tangent, the two opposite angles are always have the same tangent. It's actually why it's pi periodic. They're pi apart and they have the same tangent. So it could be this terminal ray or it could be this terminal ray. And that's it. That's the only place where y is equal to minus x. So that you get tangent as -1. And this point right here, how do I get y minus x equal? Well, it's 45, 45, 90 triangle. This has to be square root 2 over 2 on this side and square root 2 over 2 on this side, so that the coordinates are square root 2 over 2 plus for x and this time minus for y. That makes an angle here in the triangle of pi over 4. That's the triangle angle. We always make triangle angles positive since we don't need the negatives there. But the angle in standard position is actually minus pi over 4, right? Because we're taking it clockwise. Why don't I take it this one? Way around here, this way, 7 pi over 4.
Because you'd be dividing by
Yeah.
combined.
The answer is that we're looking for the unique angle between plus and minus pi over 2 that has that tangent. This would be 7 pi over 4. That's way big, right? Well, I have to go this way to minus pi over 4. So we'll say the arctangent is minus pi over 4. And what you find in these cases where you take an inverse trig function of the corresponding trig function of an angle, you either get that angle back or you get the angle in the appropriate quadrant that has the same value as this one. So we're asking what angle has the same tangent as 3 pi over 4, but is between here and here. And that's what we found. The angle with the same tangent, -1, as 3 pi over 4, is minus pi over 4. So you can think of it that way in the short if you forget this process, but that's how I would do this. Is calculate the tangent, and then say, what's the arctangent? That's the angle between here and here that has that tangent. Suppose I gave you this one. This isn't on the practice set there, but suppose I asked you to calculate the cosine of the arc sine of 1.5. What are you going to put? Trig function, the inverse trig function, we said you should draw a triangle, but I'm not on this one. Why not? I'm going to draw a triangle on this one. because the arc sine of 1.5 is undefined, right?
Why is it
Saying that the arc
undefined?
sine function, the values of x you can put in, is minus 1 to 1. Minus 1 less than or equal to x less than or equal to 1 is the arc sine of x domain. You can't put in any other numbers. You can't put in 1.5. In this case, it would behoove you to put it in your calculator. It'll tell you domain error, and then you say, oh yeah, okay. Even on this one, it will help you on the calculator. Some of the calculators will do this one exactly. All right, so if you have a calculator, check it on there, but I want to see your work. I'm liable to ask you to show me the unit circle calculation. Just draw a picture like this showing the two angles. But what you can do is do this by hand, check it on the calculator, and even if you have a decimal calculator and don't get this exact answer, you'll still see when you calculate minus pi over 4, and on a calculator, you take arc tangent of the tangent, that you get the same number. Just make sure your calculator is in radians mode, so it doesn't get you something crazy. So this might happen too, where you get undefined, you put in the wrong number that doesn't fit in the domain. Here's something, these first couple, I want to make sure I ask you some graphing problems. These are very important in lots of sciences. I want you to graph a trig function somewhere in here. Let's try one of these. Do you have a preference between either column here? The harder one maybe. Y equals minus 4 cosine 3x minus pi over 2. I think this is the harder one, plus 4. And I suppose I say sketch the graph. It's all fine to check it on the calculator, but if you do it on the calculator, it won't tell you the exact points. So I'll say sketch and plot 2 periods at least, including at least 5 exact points. That's to make you do it by hand and not just so you can use your calculator. Exact points can be very important actually in wave analysis, for instance. When you want an antenna, you want to build a standing wave, you have to put in the exact frequency. If you're a little off, it doesn't quite work as well. Right? So that's 2 periods of 5 exact points. Here's what we can do. Also, cosine's harder than sine. So this is what you do is you take the equation and look at it to figure out what the 4 numbers are. A is whatever multiplies the sine or cosine. B is whatever multiplies x. C is what's subtracted from bx. And D is what's ever added on at the end, right? So you just put A, B, C, D, and from the 4 letters, you find those 5 properties. The first one you can say is the shift. I like to call it the shift point. That's my terminology. And we'll say the shift point is C over B D. Just memorize that. Otherwise, you have to figure out all those graphing, stretching, and shifting, and it's complicated. It's easier to memorize this one for trigonometry because this comes up all the time. C over B D. Well, that's it's pi over 2, whatever's subtracted in here, right? So it's not minus pi over 2, it's plus pi over 2, all over 3. And then you have to be careful, and D is 4. When you divide these, you might think, oh, that's pi over 6, or maybe it's 3 pi over 2. What is it? Do the quotients carefully. If you've got a whole number in the bottom, you rewrite 3 as 3 over 1, and you take top times bottom over middle times middle, or top times the reciprocal of the bottom is the same. And this comes out to be pi over 6, 4. So there's the shift point, and now we can start sketching this thing, right? Once you have the shift point. That's where the origin moves to from the natural cosine function. So I'll go over pi over 6 to one side, maybe like that, about a half, right? Pi is about 3. and then up to 4. You don't have to scale the axes the same as long as you label them correctly. So maybe there's pi over 6, 4. And now what you can do is find the amplitude. The amplitude is not negative 4, what is it? Yeah, it's 4, exactly. It's the absolute value of A. So it's plus 4. Amplitude is always positive. And then the period for the sine, cosine, and the reciprocal, secant and cosecant, it's 2 pi divided by b. But if I give you a tangent or a cotangent, what would the period have been?
Is it pi over b?
Pi over b, yeah, because the natural period of those is pi, and the stretching factor of 1 over b, yeah, they're pi over b. The other 4 functions here are 2 pi over b, exactly. We'll take 2 pi over b is 2 pi over 3 is my period. 4 is my amplitude. Pi over 6, 4 is my shift point. And then finally, I want to ask, I said 5 properties, 2 of them in the first one. So I guess I should say 4 of these. Whether it's flipped. And A is negative, so it is flipped, upside down. All right, now I can try and sketch it. Start at the shift point, go up and down by the amplitude, right? Amplitude is not from the top of the wave to the bottom, it's from the middle to the top or the middle to the bottom. So if the midline, the book likes to call it, that's not used by everybody, but I think it's a nice term. Midline. Go up 4 units, the amplitude, and you can draw the top guideline for the wave. And go down 4 units, and you can draw the bottom guideline for the wave. Evidently, these are at y equals 0 and y equals 8. Now, since it's a cosine, you're going to start at the top or the bottom, directly above or below the shift point. Sine is easy, it goes right through the shift point, right? That's always easier. That's why I picked the cosine, it's harder. Does it start at the top or the bottom? Starts at the top. If you didn't flip it, starts at the bottom if you did, right? Since we flip it, we're going to start at the bottom, directly above the shift point. It starts right here. At this point, pi over 6, 0, and we have one exact point already. So on the bottom guideline, directly below the shift point is where you start a flipped cosine. Start at the top. If it's unflipped cosine, start at the shift point if it's a sine. Going up this way if it's not flipped, going down this way for the sine if it is flipped. All right. So now I'll start that. Now I'll put in the period is 2 pi over 3. I'll go out to about here. And the idea is 2 pi over 3 is the period. And at that point, I'll sketch another point corresponding to the start of the cosine wave. It starts here, 1 period later, 2 pi over 3 later, it'll be at the same y value. So this must be the point pi over 6 plus 1 period, 2 pi over 3. And the same y coordinate, 0. So there's another exact point. I just have to do my quotients here. Now, how do I add these? Yeah, common denominator. I would call this is pi over 6. The least common denominator is 6. So I'll multiply this one top and bottom and call it 4 pi over 6. And this point is exactly 5 pi over 6, right? 1 plus 4 is 5 pi over 6. So 5 pi over 6, 0 is this point here exactly. Now I have 2 exact points. And that's where it completes 1 period. So what I have to do is start here, go all the way up to the top, which it reaches halfway across, all the way back down to the bottom, and there's 1 period of the cosine wave. Now I was asked for 2 periods, so what do? I can do another 2 pi over 3 this way, or I can do 2 pi over 3 back this way, and it doesn't matter. Let's do it this way just for fun. 2 pi over 3 this way takes me to the point with coordinates pi over 6 minus 2 pi over 3, 0. And then I do my fast quotients here again. Pi over 6 minus 4 pi over 6, 0 is minus 3 pi over 6. 0, which reduces to minus pi over 2, 0. That's this point right here. And I plot that one because that's at the end of the next wave. But what I'm going to do is draw this correctly. I'm going to go up to here. This is close enough. I would count it correct on the test, but I'm going to try and make it a little more accurate just for, since it's a demonstration. Something like that. All right, so you come up to here and back up to here and back down with period 2 pi over 3 again, finishing at minus pi over 2, 0. So there's 2 complete periods. And now I can fill in the details in between. What is this point here? Well, what you do is you quarter the period. If this is 2 pi over 3, then this is pi over 6, pi over 6, pi over 6, pi over 6, because 1/4 of this is pi over 6. In other words, this is pi over 6, and we found this is 5 pi over 6, so it must be 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. So this is 3 pi over 6, which is also known as pi over 2. This is 2 pi over 6, which is also known as pi over 3. And this is 4 pi over 6, which is 2 pi over 3. And so you fill all this in just pi over 6 apart. Each one of them. It breaks it up into equal parts where it crosses the midline, where it reaches the top, where it reaches the midline, and where it reaches the bottom. This must be pi over 3, and since it's the midline, 4. This one must be pi over 2, or 3 pi over 6. And since it's on the top guideline, 8. This is 2 pi over 3, or 4 pi over 6. 4, midline. There's 1, 2, 3, 4, 5 exact points. I have another one here. I can calculate one here. This actually goes right through this point at 4, right? Because it's pi over 6 this way is 1/4 of the period. It's supposed to reach the midline. At minus pi over 6, it has to reach the top. We can get that one. At minus 2 pi over 6, which is minus pi over 3, we would reach the midline again. And at minus pi over 2, we already found is where it would wait another period. So you can actually get 9, I guess, exact points on the 2 periods if you want. I won't ask you for more than 5. It's too tedious. There's how you sketch 2 periods of y equals minus 4 cosine 3x minus pi over 2 and 4.
Professor,
Yeah.
how did you go about finding the increments at which you wanted to place points?
Yeah,
Like,
the period is 2 pi over 3.
Mm-hmm.
I'm going to divide it into 4 equal parts. So parts are 1/4 of that. They're 1/4 of 2 pi over 3. So 1/4 times 2 pi over 3 makes 2 pi over 12 or pi over 6 apart.
Okay.
2 pi over 12. This is pi over 6. So I know they're pi over 6 apart. So if this is pi over 6, this must be 1/4 period is 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. That's what I did. That's kind of fast.
Okay, gotcha. Thank you.
Yeah, you're welcome. Each of these then are pi over 6 apart. Question? Sorry, my speaker volume is down again for some reason. Comes up pretty high. There's a bunch of these, and I can never figure them all out. Okay, was there another question? I can't seem to adjust the volume as well as I'd like sort of for you. Thanks. Okay. If you get another question, go ahead. But I'd like to be able to do something like this. One of the important topics of the course. Well, if I go the other direction, like problem 2 here, let me put it up. Put the camera in that direction because it's harder to draw. There it is. Suppose I gave you this picture. And I said, what equation gives you this wave, this trig function graph? So this is number 2. Find the equation. I'll leave the camera pointed here for now. How do I find this? The idea here is to take the properties and deduce the letters instead of from the letters deducing the properties. So what are the for instance, the shift point? What's a good shift point? When you do it this direction, you always want to pick a shift point that's either on the midline, like here, or here. It goes right across a grid point there. Or it's at a maximum or a minimum, right? The top or the bottom of the wave. So you want to find one of those that's exact. Maybe it's not quite clear where this one is. It's kind of in the middle of this one. But this one, I would say, goes exactly through the point minus pi 0. So we could call that the shift point if you want. I'll write it here and I'll put it on the camera in a minute. We'll say minus pi 0 is shift point. Then what's the amplitude? Have to be careful, look at the scaling, because I put this every half unit instead of every unit. That's the grid line. What's the amplitude? Amplitude goes from the midline to the top, right? So it's 2, 0 to 2. Or from the bottom to the midline, also 2. Right? So the amplitude is equal to 2. Then the period, what's the period? This is a little tricky. I threw a curve at you on this problem. Sometimes it's really easy to tell just by looking at it, but it's kind of hard to tell here. Right? Doesn't quite go across this grid line or this one, but it seems to go across this one. What you're going to do is a couple of different things. Easiest one, I think, is say, go all the way to top, all the way down, bottom, back to the middle. That's one period, right? But it's not quite on the grid mark, so I can't call that the exact period. I'll go all the way to the top and bottom, back to the middle. It's not quite on that one, but all the way to the top, bottom, and middle, it hits this one exactly. So it does 3 periods. 1, 2, 3, going from here, minus pi to pi. So 3 periods is this length from minus pi to pi, which is 2 pi, right? And then finally, if I start with this as the shift point, minus pi 0, this is a sine wave, right? Because sine wave goes through the midline, and a cosine starts at the top or bottom. So I'm going to make it a sine wave. I'll call it sine function, rather than cosine. And it's not flipped because it goes up through the shift point. Now I'll remove the camera. And having to use those properties, I can try and use the letters to go with them. How do I make a sine function with this shift point, this amplitude? Period deduced from here, if you just divide it by 3, it says that the period is 2 pi over 3. But we said there was 3 periods between minus pi and pi, so 3 periods over the length of 2 pi. Divide by 3, get the period is 2 pi over 3. Here's what you can do. You can say amplitude is 2 and it's unflipped. What does that tell you? Unflipped amplitude 2. Yeah, it's positive because it's unflipped. And A is 2, right? So it says A equals 2. Amplitude 2 means A is plus or minus 2. If it's unflipped, it's plus 2. So there I've got amplitude is 2 from those two. Now, the period is 2 pi over 3. What does that tell you? Well, we know the
Professor?
period is 2 pi over B since it's a sine wave, right? That tells you 2 pi over 3 is equal to 2 pi over B, right?
Professor,
Yeah.
how did you get 3p equals 2 pi?
Oh, from the graph, let me put it back. It's sneaky on this one. I may not throw such a curveball on the test, I don't know, but what I did was I said, if you start at minus pi, the edge of the graph, it's right on the middle midline, and it finishes right here at pi. So it's 1 pi, 2 pi is how far it goes in x, and during that time you go 1, 2, 3 periods. So 3 periods in 2 pi length is 3 pi over 2. 3 periods equals 2 pi. Right? 3 periods when it goes 2 pi length.
Okay.
Yeah, that's the trickiest part. All right, if 3 periods is 2 pi, then divide by 3 and you get the period is 2 pi over 3. All right, so there's that one, and this tells you then by, a little algebra, you cancel the 2 pi's and you get 1 over b equals 1 over 3. Evidently, b equals 3. Now, minus pi over 0 is the shift point, tells you that c over b is equal to minus pi 0, right? Our previous comment, the shift point is always c over b, but we observe from the graph it's minus pi 0. So that tells you that d equals 0, right? The second point of 0 tells you that d equals 0. And it tells you that c over b, oops, not boxing yet, must be minus pi. But b is 3 from the other part. We'll put this in here and you get c over 3 is minus pi. Doesn't look right. Doesn't look right to me. Yes, it is. It just doesn't look like I remember the answer. Okay. So, all right. So if c is minus, c over 3 is minus pi, then you multiply that by 3. So I just put these two things together. C over b is minus pi, and b is 3. I just plug it in. So c over 3 is minus pi. That tells me that c is minus 3 pi. That's what that says. That's why it doesn't look right. No, actually, this will work, but it's a different answer than is on the answer sheet. There's an infinite number of equivalent answers. This will work. Let's just call it this then, since I did it this way. I just used a different shift point on the answer key. This will be a good illustration that you can get different answers. All right, so now I've got A, B, C, D. I'm done, right? I just wrote y equals a sine, because we said it's a sine function because it goes up through the shift point. Bx minus c plus D, so it's y equals, let's see, A was 2, sine bx will be 3x, minus c is minus a minus 3 pi becomes plus 3 pi, plus D is 0. There it is, and we can scratch this off and say, here is a perfectly good answer. And it's not the same one that's on the answer sheet, that's okay. It actually gives you the same graph. And remember, what you can do is you can add any multiple of 2 pi here, and it will be the same graph. So you can also put sine 3x plus pi, and it would still be the same graph. Or if you put plus 5 pi, it'd still be the same graph. Add any multiple of 2 pi, and it's the same. So you don't have to put 3 pi here. You can put pi or something to be easier. And then also, if you add pi here, it's equivalent. It flips it upside down, so it's equivalent to putting a minus out here. The answer on the practice test gets rid of the 3 pi and puts a minus out here, and it's the same graph. So I won't worry about you getting exactly the same equation. This one's just as good. Maybe I should point out, though, the answer key got its answer, just in case you're interested. If you were to instead pick this point here for the shift point, 0, 0, that's a nice easy shift point to pick 0, 0, right? Because that makes the shift 0. If you do that, now it goes down through the shift point, so it's a sine wave flipped. If you do the flip sine wave with this as the shift point, then you'll get the answer that's on the sheet. You'll get minus 2 sine 3x for this graph. All right. Everybody feel comfortable with the other graphs there, or in particular that's looking at? I'll try this one here. One of these. Evaluating inverse trig functions. Here's something I'll probably have you do, like 5b there. I don't think this is as hard as the ones we've been doing, but it's still something I'd like to ask you. I want to make sure you can evaluate inverse trig functions exactly. And again, on some calculators, you can do this exactly. Well, let's do this in degrees this time instead of radians. 5b. What is the arc sine of arc sine of a half? Find the exact expression in degrees.
We can't see what you're writing.
Yeah, I'm actually aware of that for a change. I'm going to move in a second. Thank you. There we go. I know I forget that a lot too. Find exactly in degrees the arc sine of 1/2. Remember what you do when you want to evaluate an inverse trig function? You ask yourself what angle has that sine? What theta within the range of the arc sine? The arc sine always gives you a number between minus pi over 2 and pi over 2. We said that's the piece of the sine function you flipped. Has this sign, and that'll be the answer. So on the test, I'd like you to show me like the unit circle or something. Say, I want the sine of theta equal to half. The sine of theta is the y coordinate, right, on the unit circle. Well, on the unit circle graph, I'll see it's the horizontal line, y equal to half, right, halfway up to the top here. And then I observe that there's only 2 points on the unit circle that can have that y coordinate. Hence, only 2 possible terminal rays, that one or that one. Then you ask yourself, what angle gives one of those terminal rays and is between plus and minus pi over 2? Well, it can't be this one because it's bigger than pi over 2 or less than minus pi over 2 to go over there either way. So I throw that one out and I say it must be this one. It's not all the way around in here. That's too big. That's more than 2 pi. It must be this one right here, whatever that is. It is what? We drop the perpendicular. Since it goes from 0 to a half, this side is a half. Since it's a unit circle, this side is 1. I know what it is. It's a 1/2 square root 3 over 2, one triangle. The Pythagorean theorem would prove it. But you memorize it, and then you don't have to do that. So it's a 30, 60, 90 triangle. This one must be 30 degrees. Right? So the arc sine of a half is actually 30 degrees. And if you run that even on the cheapy calculators that don't have exact modes, it'll still tell you 30 degrees exactly, so you can check that one by hand. But any inverse trig function of a number that comes from a special angle, I expect to be able to do exactly by hand. Show me a picture and write the answer either in degrees or radians. Test I might give you radians. Feel comfortable with the word problems? There are some word problems that aren't on the practice set also. I don't know if you want to look at some of those. Well, I'll tell you what, I'll do one more hard one that's on here since review, we want to make sure we cover most of the hard ones. How about number 4 then? You probably can't see it online, but I'm going to move this over for a minute. There it is. This time, look at the graph and decide what's the trig function that creates this graph. It's not a sine or cosine because it's not a wave anymore. It's this cyclic graph that repeats. What has that graph? And there's actually an infinite number of answers here. Remember, the tangent and the cotangent are just each other flipped upside down and shifted over. That was how we derived the cotangent graph. We flipped the tangent upside down and slid it over pi over 2. So you can use either a tangent or a cotangent to write the equation for this. Which one should we use? It's up to you. The easiest way is to use either an exact point for the crossing point here, or an exact point for the asymptote. That's what you want to find. What's something that's exact in here that I can deal with? Oh, x equals pi over 3 is labeled. So this asymptote is x equals pi over 3. Here's another one, x equals minus 5 pi over 3. So let me graph those over here. There's one of these. And here's the next one. X equals minus pi over 3. And the graph goes down like this. And you can do one of two things. You can either go by the asymptotes, or you can go by the point halfway in between, which it crosses the x-axis halfway in between. And what's halfway between minus 5 pi over 3 and minus pi over 3? You could say, well, this is minus 3 pi over 3, right? Halfway in between, just average these, just plus this over 2. So you could make the shift point there, or you can make the shift point right here on an asymptote. Either way you like it. Suppose I do this, since this is already labeled, and say, here's the shift point, minus pi over 3, 0 is the shift point. But you do the same thing we did with the sine and cosine, where you see the graph and figure out what the letters are. You just use the properties to introduce the letters instead of the letters to introduce the properties. So this will be the shift point. Now, instead of amplitude for a tangent or cotangent, we'll say what's the stretch factor. If you look at that, it looks like there is no stretch. When it's halfway between, I know you can't see it online, halfway between the asymptote and the midline. Take a remote with me to do this. When it's halfway between this crossing point and the asymptote, it looks like it's crossing one about there. So it looks like it's unstretched, right? If the stretch factor is 1. Instead of saying amplitude, we'll say stretch factor. Absolute value of A is 1. Since the graph goes down to the right, we could say it's a cotangent function. And if I put the shift point on the asymptote, that's good for cotangent. And then unflipped, since it goes down to the right, or you could use a flipped tangent if you preferred. Okay, so unflipped cotangent, stretch factor 1, shift point here, and then I need the period, right? The period, if I look at the graph, it went from minus 5 pi over 3 to pi over 3. So you subtract those. You take the larger one minus the smaller one, and that gives you the distance between them, which will be our period, right? I'll go from one asymptote to the next is one period. So minus pi over 3 minus 5 pi over 3 leaves 4 pi over 3, right? 1 minus a negative 5 and 1 plus 5 is 4 pi over 3. And so I take that into account. Now I've got enough to figure out all the letters. Shift point, the stretch, and then we said unflipped and period. All right. Now we can get it. Since it's a cotangent function, its period is pi over b, not 2 pi over b. So this one says that pi over b is equal to 4 pi over 3, and we just have to solve that for b, right? So I'll flip these upside down. If these are equal, their reciprocals are equal, I'll write that b over pi is 3 over 4 pi. And then I'll multiply by pi and get b is 3 pi over 4 pi. Cancel the pi's is 3/4. So there's b is 3/4.
Shouldn't the period be 2 pi?
Did I miss?
Yeah.
Calculate? Yeah, I missed subtracted, right?
Well, the x on where the tangent goes to negative infinity, it's positive.
Oh, that's why I put minus pi over 3. This is pi over 3. I wrote minus pi over 3 here, and it should have been pi over 3. That's what I did wrong. Let's copy that. Pi over 3 here. Thank you so much. I'm going to get the wrong answer, and I'll have to figure it out. The mistake is always right at the beginning, right? Pi over 3 and pi over 3. Get rid of the minus there. So I mislabeled that. Yeah, now pi over 3 minus a minus 5 pi over 3 is 6 pi over 3, or 2 pi. There we go. So period 2 pi. So I need to fix this. Going the wrong direction. So period is 2 pi instead of 4 pi over 3. Tells you that 2 pi over b is equal to 2 pi over b for cotangent is equal to 2 pi. Now flip them upside down. B over pi is 1 over 2 pi. Multiply by pi, and you get b equals a half. Cancel the pi's if you like. So there's b. We said there was no stretch, so the absolute value of a is 1, and it's unflipped. So absolute a is plus or minus 1. It's unflipped. A must be 1 of these. Now from here, this is the shift point is c over b. D tells you that d equals 0. Immediately. And then over here we have c over b, if I run this around. C over b is negative pi over 3. But we just found out b is a half. So this is c over a half equals negative pi over 3. Multiply both sides by a half. And you get c is minus pi over 3 times a half. Remember how to multiply fractions, top times top over bottom times bottom. Is minus pi over 6. So there's C, B, A, and D. We've got it now. Let's see if I move this a little further maybe, huh? And we said it's a cotangent function since we did call it a flipped function.
Professor, when you're finding your C, shouldn't your pi over 3 be positive still?
C over B should be the shift, and the shift was, oh yeah, because when I forgot when I fixed this, I didn't shift it up here, did I? Let's see. X is pi over 3 is the shift. Yeah. Yeah, I didn't fix it here. That should have been pi over 3, pi over 3, and pi over 3. I had all three of those with the negative ones. I just copied it once. Yeah, thank you. That should have been pi over 3, and the shift is pi over 3. Yeah, and get rid of all these minuses. Once that one minus is in there, it's like lying, right? Oh, what a tangled web we weave when we first practice to deceive. It just carries through the whole problem of lie, right? All right, pi over 6. Y equals a cotangent bx minus c plus b. Thank you very much, by the way. A is 1, b was 1/2, c was plus pi over 6, so we subtract c, and then plus d was 0. The graph, the answer hopefully says cotangent 1/2 x minus pi over 6. Or it might say tangent if I pick a different shift point. I can't remember what I did now. Yeah, I use tangent instead. So this is a good answer too. And the tangent answer in the back comes from choosing this. If you choose this as the shift point, halfway between these, you average them to get this one. It's on the x-axis, so the y-coordinate is 0, but then you get -5. Let's see, yeah, -5 pi over 3 plus pi over 3 all over 2 is this one. Gives you -2 pi over 3, right? Over 2. -4 pi over 3 over 2 is -2 pi over 3. So if you use that one, I think that's what I use for the tangent there. Apparently I used the other one, but this would work too. So if you want to use tangent, you could use this for the shift point. It wouldn't still quite give you what's on the answer key. All right, any questions on this one? Can you do something like this? Use either a tangent or a cotangent to write an equation for a graph? Well, we should do at least one applied problem. We've looked at both problems just like this before with different numbers, actually. But we can look at the ladder problem. I'll give you some sort of word problem. I think on the test I'm planning to, but I haven't written it yet. Could be one of these. Could be something else off the practice sheet. I make something similar to something you've seen. Suppose we do this one. This is number 8. I think I'm still on camera here, but I better check. You have a ladder. Always on these applied problems, draw a picture. Leaning against the building. Unlike the homework, it goes up to the 3rd floor. And the ladder is 17 feet long. And so you draw the picture and label everything you're given. Reaches to the bottom of the 3rd floor window, 15 feet above the ground. So this height here is 15. Always assume, unless we say otherwise, that the ground is level and the building is horizontal. So it's 15 feet here, 17 feet here, and it's asked this time instead of the angle between the ladder and the building, this problem asks what angle in degrees does the ladder make with the ground? So what's this angle theta? All right? Here's what you do on these applied problems in a triangle. This is actually one of the most crucial things in the whole course is being able to solve these kinds of basic right triangle problems. You write an equation We sort of did this on the first test, but this is it was without inverse trigonometry to do exactly this problem. Write an equation relating the given numbers, two given numbers, and the unknown number that you want. That's what we did on the first test. What's different here is we're going to have to use an inverse trig function for this kind of problem. I have this angle and these two sides. What relates this angle to these two sides? What trig function?
It's over.
Cosine.
Yeah, it's sine, opposite over hypotenuse. So I'll say sine theta equals 15 over 17. In a triangle, in a right triangle, you can just take the inverse sine of each side. And you take the inverse sine of the left, you just get theta because they undo each other in a right triangle. Is the inverse sine of 15 over 17 by taking arc sine of each side. There's the answer exactly. Well, we want to run it on the calculator. I said round to the nearest 2 decimal places. So round means now you're supposed to put an approximate. Not my, I had my calculator in hand just for this. Maybe I set it down when I went back, huh? All right. But you have to put your calculator then into degrees mode. It's very important since you're asking for degrees. And then you push second sine instead of sine. Second sine gives you the sine, and second sine gives you the inverse sine because it's in color over this one, same color as this key. 1/5 divided by 1/7. You may need to close the parenthesis depending on the calculator. And then push enter. So sine of the number gives you the sine, but second sine gives you the inverse sine. That's I'm going to set my calculator down somewhere. I guess I'll leave off the actual computation. All right.
It's 61.927.
Oh, thank you. So if I get 61.927, and other stuff, I suppose, then you round it off to 2 decimal places by taking, since 7 is greater than 5, you round this up to 61.93. And it's degrees. Make sure you put your degree sign when it's in degrees. If there's no sign there, it's assumed it's radians. And no degree sign. Must be radians. All right. Suppose I asked you to evaluate this one. What is the inverse secant of minus square root 2? I think we have just enough time for this one. That's number 5C. Inverse secant of minus square root 2. There's no inverse secant in the calculator. And I asked to do this exactly. So even if you have a calculator that does these exactly, you have to learn something in the course, right? How can I evaluate an inverse secant? This is giving an angle whose secant is minus square root 2. So I can call it theta. Well, this is asking what theta within the range of the inverse secant has secant theta equal to minus square root 2. Right? That's what the question is when you ask for the inverse secant. And the inverse secant gives you an angle between 0 and pi, or pi over 2, or pi over 2 and pi. It's essentially between 0 and pi, but not equal to pi over 2. Because the inverse secant of pi over 2 isn't defined. Well, instead of finding what angle has secant, do the reciprocal and say the reciprocal of secant is cosine. The reciprocal of this is minus 1 over square root 2. What angle between 0 and pi, excluding pi over 2, has cosine equal to minus 1 over square root 2? We can do this. What is it? might memorize it already. But it might help you to write it like this, right? Rationalize it, multiply top and bottom by square root 2, you get minus square root 2 over 2. I recognize that. That's a special triangle, right? Cosine is the x-coordinate in any case. So you put it in terms of cosine instead of secant. Then this is the x-coordinate is minus square root 2 over 2. It's about minus 0.7, like that. And there's exactly 2 points on the unit circle with that x-coordinate. One's here, and one's here. And which one is it? The angle between 0 and pi, right? So it's between here and here. Inverse sine and tangent give you an angle in the first or second quadrant. Inverse cosine gives you first or fourth quadrant. Inverse cosine gives you first or second quadrant. So it must be this one here, not this one, because that's the wrong quadrant. It must be this angle right here between 0 and pi. What is it? Well, it's the one that has cosine. The x-coordinate is minus square root 2 over 2. So this side must be plus square root 2 over 2 in length. This is one, oh, it's a 45, 45, 90 triangle, right? This is pi over 4. Did I say radians on that? No, I said degrees. All right, so we'll call it 45 degrees. And if that's 45 degrees and all of these add up to 180, this must be 135 degrees. So the answer here is 135 degrees, and you can get it on the unit circle after first writing it as a cosine problem. All right, that'll finish it. Best wishes on the test next time. Send me emails if you have more questions or maybe laugh.